All right. You recall that what we were trying to do was to show that by the standard constructions of Euclidean geometry interpreted in analytic geometry, we could do no more than add, multiply, subtract, and divide, and in addition take square roots. And that conversely, we could do all of those things with the standard construction of analytic geometry. We looked at how we would add, subtract, multiply, and divide. We haven't yet looked at how we would extract a square root, although I remind you that Descartes, for example, shows us how to do it. And what we were doing was running through the other standard three constructions, which would take intersection of two lines. Intersection of two lines just gives a point, and we saw last time that that point was, from our algebraic point of view, not of much interest, that we could calculate it in terms of the original equation of the original two lines. So let's come now to the intersection of a line and a circle, which is in some sense the critical construction, and let's just observe that that really involves taking a square root. All right, so we want to begin, and we can do one of two things. Either we can choose our coordinates appropriately so that the origin of coordinates is at the center of the circle, or if we like, since we know how to translate a circle, we can just translate it from its center, which is at some point AB, which is known, back to the origin, do everything there, and if we're really very careful, then afterwards we can translate everything back, just by adding, as we saw, the coordinates of numbers A and B to the whatever we get. So it's a circle with an equation of the origin, and we know that means this is a point on the circle, this is x, this is y, sum of the x squared plus y squared is the square of this distance, which is called the square of the radius of the circle. So what we want to do is to find out what these 2 points are. We take this circle and we pass a line through it. So the line will be given by some equation that we know. And unfortunately, I chose AB here as well as up here, so that's a new A and B. Now, this is the equation of a line, and we can't just have C equals 0. That's not the equation of a line. So either A or B is not 0. So let's just treat the case A. And then we can just solve this for x in terms of y. So x is minus by plus c over A. And then to find out then what the equation is for y, we just substitute in this, x equals minus by plus c over A. We get this equation, which I rewrite, multiplying through by a squared that way. And then I write this out, by plus c all squared has a by times by, so b squared y squared in it. So I get a b squared y squared, add to that, which is that. And I get a byc twice, because I have to by times the second c and c times the second by. So that's that. And then I get a c squared when I multiply out. And then I bring this over, minus a squared r squared. So for y, I have a quadratic equation to solve. I solve it by the usual formula that we derived, and I get rid of it. There are several factors of 2. 2bc for this coordinate of y, it comes here. And here I have the usual formula, 2 times the coefficient of y squared. And that's that. And then I have plus or minus, and again I get 2 times the coefficient of y squared. Then, and what the usual formula is, if you remember, b squared minus 4ac. So this squared, 4 times this, then times this. And all those 4's and 2's cancel each other, and I just left with that. So the point is that intersecting those 2 things, we get, apart from this, from some multiplying, we have to calculate a squared, b squared, multiply b times c, some dividing and some adding and subtracting. the essential thing there is a square root. So intersection of a line and circle just involve taking a square root, and they won't give us any more, and they give us that much at least, and that's the observation of Descartes, if you like. Let's just do Descartes' diagram as an example of what we had. So Descartes wants to work things out so that this number is 0, so that this number is 1, and so that this number here is a given number. So what he does is he says, let's take a circle with center at the origin, takes the diameter, 1 plus d. D is the number whose square root he wants to find, so its radius is half that. He takes that line that I have to be a vertical line, takes it through the point here whose x-coordinate is minus d plus 1 over 2. So that means that x will have to be equal to minus d minus 1 over 2. So that's the equation of the line. It's just a determination on x. So it's that line. The circle is x squared plus y squared equals r squared. That's r. So we plug everything in down here. So in particular, we see that a is equal to 1. There's no y isn't even there, so b is equal to 0. And c is d minus 1 over 2. Well, b is equal to 0, so that term goes away. A is equal to 1 and b is equal to 0, so this is 1. So we get y is equal to plus or minus b squared c squared. B is equal to 0, so b squared c squared is not there. Then if you work out this number, b is equal to 0, I have minus an a squared, but a is 1, so this is just minus c squared. And you have to work out what we're left with, minus c squared minus r squared. We calculated r squared minus c squared. That's r squared. That's c squared. Now, if you expand everything out here, what you see is that the squared terms here, d squared, cancel with the d squared here, and what you're left with is just d. So that's just what Descartes does, is just works, in particular what Descartes does. He works that out in particular so that the y-coordinate here, in other words, the length of this line, as he would say, is the square root of d, for d, any given positive number. So there we know now that we can calculate the square root of d with Euclidean constructions. That leads us to see what happens with the intersection of two circles, which is the last possibility. And it turns out that it doesn't appear to give us anything new, except you remember that we have to do such a simple thing as to divide by 2, we have to intersect circles. I pointed that out before. So we just run through the algebra. So once again we can translate and move back afterwards. So we choose the circle to have its center at the origin, or choose the origin to be the center of one of the circles. And then we choose that x-axis, or this horizontal axis, to pass through the center of the other circle. So that our two circles are sitting there. That involves a rotation, and we know that that involves a choice of axis, if you like, or just a rotation of the given axis, so that it passes of the rotation. We fix the center of this circle to be at the origin, and wherever the center of the other one is, we can just rotate the line passing through the two centers so that it's horizontal. We know how to do that. That's just, as we said, that's just multiplication. So the first circle has an equation then. There was center of the origin. X squared plus y squared equals some radius. And the second, we suppose, like just for simplicity, but we can arrange it just by choosing the length scale right, has origin here, center here at the point with coordinates 1 and 0. X coordinate 1 and y coordinate 0. So we take the coordinate centers at 1 and 0, and that's the equation of the second system. We have to solve these two equations simultaneously. So this one and this one that one. Well, here's y squared in terms of x. So we substitute this into that. We're left with this equation. The funny thing happens, namely, here's x squared. When you multiply out, we get x squared. It cancels with that x squared. We get x times minus 1 twice, which is minus 2x. We take that over to the other side. Okay, I will take it over to the other side. It gives us 2x. And that leaves us on this side r squared, a plus 1 coming from squaring this minus 1, and little r squared, a plus 1, and we brought this r squared back, and we get minus r squared. So we have this equation. So x is, we don't have to do anything to get x, we just have to do some multiplication. And then once we have x, then here's y, which y is the square root of this expression. There's x, all squared, and then we can rewrite it if we like in those terms. We don't have to. The point is that all we do is get a square root. We don't do anything more. We have take the intersection of two circles. It doesn't give us anything more, provided we've agreed that we can add, subtract, multiply, and divide. And this here is neither here nor there for our purposes. It's just meant to say, with numbers, that sometimes if the two radii are too little too small, the circles won't meet at all. And this number will be the square root of a negative number, so it doesn't correspond to something real, if you like. Or it doesn't correspond to a real intersection. Or sometimes capital R is too big in relation to small r, and then the second large circle just engulfs the small one. And again, there's no intersection. So it has to be only for certain capital R and lowercase r is there an intersection. Otherwise, that number, the square root we're trying to take, is negative, and it doesn't have a geometric meaning. All right. So that, in some sense, basically it for analytic geometry. I'm just checking this. We want to check that the person who asked for a list of the text I consulted is here. So clear that I consulted Heath Euclid. It's clear and will be clear that I consulted Descartes. I admit that this is a rather pedestrian book, but on the other hand, it's very useful in the sense that if you want to have the background on any rather lengthy text, and if you want to have the background on any given mathematical topic that's not too recent, Klein gives it, so you just have to check in Klein, and you can go from Klein elsewhere. And Boyer is perhaps slightly doubtful, but it's a large book with various things about analytic geometry in it. That's useful. And then when I get on to Gauss, there are two references. This is the main reference, and I want to encourage particularly all mathematicians to read Gauss. Gauss is much simpler than Euclid to read, I think. And then for some introduction to Gauss and some other comments on this book, of course, contains many things besides the thing that I've consulted it for on this occasion, namely the construction of the regular heptadecagon. But oddly enough, the construction of the regular heptadecagon comes at the very end. But you go to the very end without. Klein's book is a little more accessible. Klein discusses that construction. There are comments on Klein by other people, and all these comments are useful, and they give some historical background. Gauss's book is available in many, many languages. All right. It's actually here. Let me give you those two before. All right. Now, so we've done what we need to do with analytic geometry, but since I was asked a little bit about Descartes, let me just say a little bit about Descartes. It was not my intention to talk about mathematics for some very good reasons, what I'm competent to talk about. And so I really shouldn't allow myself to any digressions, but some specific questions were asked last week, and let me come to those specific questions. And first of all, what I will do is give you the answer to those specific questions that I discovered simply by reading what was immediately accessible, namely the discours. Just looking at the discours and seeing what was there, and then I will comment on the dangers of doing such things. Right? There are traps for the unwary. So, Descartes is actually quite explicit in the discours about the role of mathematics in his proposed methodology. And this methodology seems to have matured over the course of about 17 years, from 1619 when he was 23 to 1637 when he was 41. Now, I've just pointed out, it's an aside, that in intervening years he'd seen a certain amount of the world, at least in the beginning. He began life at an early age by joining the army, and he took part, I don't know in what capacity, but he took part in the Battle of the White Mountain at the beginning of the 30 Years' War. He was on the winning side, he was on the imperial side, but he didn't stay long in the army. He did travel, and in the last 9 years of that 17-year period, from the age of 23 to 41, he was in the Netherlands, which I gather from a recent review of this book about Rembrandt, who was a contemporary of, more or less a contemporary, slightly younger of Descartes. It's a very good place to be at that time for an intellectual and a scientist. A lot was happening. The Netherlands had just become basically independent and was thriving. Now, Descartes introduces the precepts of the methodology with a remark, and I quote, namely this is a fairly literal translation of what he says. He had studied little when young, among other parts of philosophy, logic, and among other parts of mathematics, the analysis of the geometers and algebra, 3 arts or sciences that seemed capable of contributing to his plan. And then he observes that on closer examination, logic served more to explain the known than to learn the new. And as for the analysis of the ancients and the algebra of the moderns, which that's his terminology, they both seem too abstract. The first 2 constrained to the use of figures, and the second, you can interpret this line as you like, to various rules and signs, out of which an art had been constructed that confused the mind rather than cultivated it. Keep that phrase in mind when I come to the very end. Now, what he proposes is an art with a few simple precepts, and I think this is the heart of his method, so I summarize them briefly. So, never to accept anything as true except that which he recognizes as clearly such. First precept. Second is to divide each difficulty that he meets into manageable pieces. The third is to proceed in his thinking stage by stage from the simple to the complex. And the fourth is to review his thinking so carefully that he was sure that nothing had been omitted. I believe that these precepts are the essence of his method. Then oddly enough, in spite of his previous strictures, he turns back to mathematics. And again, I cite the text with a more or less literal translation. It's rather long, but let me read, because I was asked what the relation was between the method and mathematics, and it's not entirely clear. Let me cite at least what Descartes said. These long chains of reasoning, all simple and easy, that geometers customarily use to arrive at their most difficult proofs, gave me an occasion to imagine that everything that could be known by men followed in the same fashion, and that provided only that one abstained from accepting anything for true that was not, and that one kept always to the necessary order in deducing one from the other, there were none so abstruse that one could not ultimately arrive at them, nor so hidden that they would never be discovered. I had no difficulty in finding the correct place to begin, the place where these precepts are obviously applied, because I knew already that it was the simplest and the easiest to know, and that considering among all those who had already searched for the truth in the sciences, it was only the mathematicians who had been able to discover some proofs, that is to say, some certain and evident reasoning. I did not at all doubt that these, in other words, the things from which to begin, would be the things they had examined, even though I'd hoped for no other profit than that they might accustom my wit to nourish itself with truths and not to content itself with false arguments. But I had no intention for all that of trying to learn all the particular sciences commonly called mathematical, and seeing that although their objects were different, they nevertheless were in accord, and that they did not treat of other things except for various pertinent ratios or proportions. This seems to be an allusion to Book 5 of Euclid, of course, that mathematicians are concerned with numbers or lengths or areas, but it's all one and the same thing. And then Descartes goes on, I thought that it would be more profitable to examine these proportions in general, and only in those subjects that would make a knowledge of them easier for me, but also without restricting them in any manner, in order to be able to apply them later to the other subjects for which they were appropriate. Then, having observed that to understand them, I would have sometimes to consider them separately, and sometimes to imagine or understand them several at a time. So, singly would mean you would consider one line and one length, for example. Several at a time would mean several lines and several lengths. Because I thought in order to consider them better separately, I should imagine them as lines, so rather than areas, or rather than numbers. Because I found nothing that was more simple and that I could more distinctly represent to my imagination and my senses. Right? And if you look at la geometry, you discover that everything he proves about lines. There's nothing about planar geometry, nothing about numbers, nothing about areas. So he wanted to represent them as lines so that he could distinctly represent them to his imagination and to his senses, but then he goes on. But that in order to hold them in my mind or to understand several at once, it was necessary to explain them with some sign. He uses the word cipher, but I think he means just signs, as short as possible. And in this way I took the best from geometrical analysis and from algebra, correcting the faults of one by the other. And that's what he says he's done. Now, should say, as everyone knows, that Descartes was not primarily a mathematician. And in fact, you can ask yourself, this is true of everyone, you can ask yourself whether he's a mathematician at all. This is a funny thing to say, but we all know that there are people who make a living as mathematicians even, give talks at international congress who aren't really mathematicians. They sometimes have trouble with the proof. In other words, they look as though they understand what a proof is, but often, if we examine them very carefully, they don't always know what a proof is. So it's an interesting question. You can pose the question, was Descartes a mathematician? Now, it seemed to me on reading the discourse that he had actually two quite different mathematical talents. He was able to discover new facts, so as mathematicians normally call new facts theorems or nowadays results. Perhaps even to prove them, and he could formulate new concepts. That seems to be clear. Now, it's obvious that I can't say, without more knowledge of the 16th and early 17th century literature, what was new and what wasn't new. Now, on the other hand, various things, looking at secondary authorities, I was assured that various things were in fact Descartes. And I give you one because it's something that many of you will know, not everyone will know, and it's so-called the Descartes rule of signs. And he gives it there. In passing, he mentions this. And I think it's a no matter who discovered it, it's a very pretty fact. I remind you of it. See, this is an equation. Let's look at it. Unfortunately, I got some signs wrong. This is rather critical here. But it's x cubed minus 6x squared plus 11x minus 6 equals 0. So that's an equation. It's of degree 3, or what Descartes would say of dimension 3. Dimension doesn't really matter, and I've taken it to be this. So of degree n or dimension n, I point out that has exactly n roots. This is something that we haven't proved. I just, in the background, I want you to keep that in mind, that it is a true fact. And the more you think about it, the more surprising a fact it is that these n roots are ordinary complex numbers that we'll come to. All right? And what Descartes' rule of signs is that the number of roots, he calls them true, he means positive roots, is at most equal to the number of sign changes. You see here, as I move from coefficient to coefficient, here the coefficient is 1, and this is minus 6, there's a sign change. Minus 6 plus 11 is another sign change. Plus 11 minus 6 is a third sign change. So here there are 3 sign changes, and that means that according to this rule of sign, this equation can have 3 roots. Well, I've done it in this way, so it clearly has is 0 for x equal 1, 2, or 3. It clearly has 3 roots. But it's a nice principle, and just some examples. For example, here I just change this. This is 1, 2, and minus 3. So the roots are minus 1, minus 2, and 3. 2 negative, and 1 positive. Now, how many sign changes there are? Well, if one coefficient is 0, and here there's 0 times x squared, we don't know whether 0 is positive or negative. So passing, we can count it as a sign change or not. So going from 1 to 0, that's a sign change. From 0 to minus 7, that's a sign change. That's 2 sign changes. So the 2 sign changes. And the doublets, in other words, when the sign doesn't change, 1 to 0 is also not a sign change. 0 to minus 7 is not a sign change, and minus 7 to minus 6. So there's 3 doublets. That means 3 places where the sign doesn't change. And so we can have at most 2 positive roots, and at most 3 negative roots, while in fact there's 1 positive root and 2 negative roots. And here, for example, there are 2 sign changes, 1 from here to here, and 1 from here to here, and 1 doublet from here to here. Doublet means the sign doesn't change. So there are at most 2 positive roots, there are 2 and 3, and at most 1 negative is minus 1. See, by the way, if you look at this simple example, there are no roots in the ordinary sense, no real number such that x squared plus 1 is 0. So the only root here, the only way we can make this 0 is to make x equal 3. So 1 positive root, no negative roots, and the 3 sign changes, but still the rule is valid. And it's a nice rule. It's a pretty rule. And one of the secondary sources, I don't know quite what it means. I don't know quite when it was proved. Claims it was first proved by Gauss, but I don't know what he means by that. But it's clear, if those mathematicians in the audience, they think how they're going to prove it, they're obviously going to use an induction and a derivative, so, which Descartes didn't have. I assume Descartes just arrived at this by induction and perhaps didn't prove it. All right? So, and let's keep in mind, so this is not germane, of course, to our discussion, except that it's good to know for later use that an equation of degree n does have n roots. So don't forget that if you don't know it. Now, that being said, I'm having an email exchange with a friend about this, and I showed him some of the things that I was going to say, and he shot back right away about the Descartes' rule of signs, that it was due to Harriot, an English mathematician. Harriot is an English mathematician whose name has been mentioned frequently of late because it's Harriot who was posed the problem to Kepler, which led to this sphere packing problem that was recently solved by Thomas Hales. So Harriot it's a known name, and he immediately shot back that it was Harriot's rule of signs, that he was the one who discovered it. Well, I said to him, Harriot died in 1621 when Descartes would have been 25. How would that have, and he didn't publish very much, so how would that have worked? He said, I've forgotten where I discovered that, and I'll have to look it up. And he hasn't come back to it yet, but he has come back with the following quote from Wallace. Apparently there's a biography of Harriot. We don't have it in our library, so I haven't had a look at it. But Harriot's book on algebra which was published in 1621. What I want to say is that Wallace, an English mathematician Wallace, had a copy of this book, and apparently, after Wallace's death, a note was discovered, a note of Wallace was discovered in Harriot's book, and this is what Wallace says. I just pass it on. This, and I said, my friend sent this to me. This treatise of Mr. Harriot's was, it seems, so well liked by Descartes, that's how it's written here, Descartes, that he hath, in a manner, transcribed the whole of it for the substance, though in other words, into his geometry, but without so much as ever naming the author, which was first published in the year 1637, that's naming Descartes, 6 years after this was first extant. So, one has to be careful. It's not quite clear who did what. You shouldn't presume on your knowledge, and I don't want to do that here. But let's just go on. I'll presume on mine. So you may presume on yours if you like. I don't want to force my presumptions on you. So let me just go on and just give you an idea, nonetheless, what is in the in La Géométrie, because it's not so dissimilar to what to our purpose, namely, wants to consider constructions. So, and I should say, by the way, that it's probably the case that if you really want to see how pertinent Descartes' ideas were, his contributions to physics and natural science are probably more pertinent than his contributions to mathematics. It's very likely that he was in mathematics. He was influenced by what was happening around him. So, as I said, our problems are, in Descartes' terminology, planar problems. Sometimes refers to them as two-dimensional problems, but that means, for Descartes, two-dimensional means that the degree of the equations that arise is most two. But they can be solved by quadratic equations. So these aren't so interesting for him. He deals with these problems briefly, as I indicated, with some illustrations in the first few pages. He's interested in more complicated problems. But there are a number of points that he makes now, whether they are his own point or somebody else's points is perhaps not so important. And let's just stress it here. The first point that he makes is that, most people know, but seems a little bit strange in our context, the restriction to the use of ruler and compasses is unnatural. It's a convention that we inherited from Euclid. The compass is simply a mechanical device. The ruler is a mechanical device, and other mechanical devices could be considered, and Descartes suggests one, and I'll show it to you just so we have it. So what we have to suggest is that the restriction to ruler, and remember at least, is that the restriction to ruler and compass has a great deal of historical importance. That's Euclid's restriction, and it's a great deal of theoretical significance, namely it's going to allow us to understand, by pursuing the points and by pursuing the analysis of these constructions, to learn a lot more about algebra and therefore about number theory. Now let me just remind you of something that I know is too far from our consideration. Suppose we had, so on a line we have point Y, A, B, C, and D, and we're interested in the case that the ratio of YA to YB is the same as the ratio of YB to YC, and the ratio of YC to YD is the same as the ratio of YD to YC. So what if we had that relation? Now, if we have that relation, then YA over YB is the same as any of these three quotients. So if we multiply them together and cancel the YB and cancel the YC, we have YA over YB cubed is equal to YA over YD. Now, one just said, it's just a question of terminology, that these three relations mean that YB and YC are two mean proportionals between YA and YD. example, if YA over YB has a ratio 1 to 2, this would mean that YA over YB cubed was 1/2. So this number, YB over YA, would be the cube root of 2. And that would mean exactly that if YA were the side of a cube, then YB would be the side of a cube of twice the volume. So this was one of the classic problems of antiquity, namely to duplicate the cube. And to duplicate the cube involves taking two mean proportionals. Now, in antiquity, people were quite aware that you could do this with a machine, various machines. You could also think of four mean proportionals, which would give you, here's the fifth root. And here's the machine. I just give it to you. It's the one that Descartes, the one that was familiar. He wants to make the point that the machine is a machine because the point is, as you know, that Descartes wants to consider a large class of curves, in particular curves that can be constructed by mechanical means. Oh, I removed this too fast. You see, Jim, I said YA should be to YB as YB to YC, and YB should be to YC as YC is to YD. You see, so we could do this in the following way. We have any angle, we put in there, so there's YA on that side, and YD on this side, what we would like is to draw a right angle here, and a right angle up there, so that this right angle exactly hits here, so that we come here, and then we go up here with the right angle and back down with the right angle, we end up exactly at B. We can't do that so easily. If we start off with YA, we can draw this right angle, we can draw this right angle, we can draw this right angle. We don't know quite where we end up. And that's because there are three similar triangles here. See, this triangle is similar to this one, and of course this one is obviously similar to the big one. So YAB is similar to YCD and to YBC. And that means this side is to this side, the hypotenuse, as this corresponding side of the slightly larger triangle is to this hypotenuse, as this side is to the hypotenuse of the largest triangle. So this is the kind of diagram you have to construct in order to have this relation. And you see how you can do it. You just have one bar and a second bar that rotates. This sits out at a right angle from it. And then this is movable. This always comes off at a right angle to this line, but the base is movable. So as you rotate this, this bar pushes that over. This bar then pushes that over. This bar pushes that over, and so forth. So you can arrange just by opening it up as widely as necessary that this point E lies anywhere you like. So that's the mechanical device for arranging that, and that Descartes just puts there. And then something that, to my knowledge, is, but I don't know, as I said, one of the secondary authorities suggested is that it did originate with him. I just give it to you because it's there, and it's one of the principal things he does, and I think he's probably quite proud of it. Because he has his analytic geometry, he can pass back and forth freely between equations and the geometry, and then he can pass back and forth freely between equations. Equation to geometry, geometry perhaps back to another equation. And what he wants to do, this is basically an arbitrary equation of the fourth degree. Z to the fourth equals AP Z squared plus AQ Z plus A cubed R. And the A is just a symbol because everything is a length for him, so he needs to have a basic length, as we said. So he could take the a equal 1. So it's basically z to the 4th equals tz squared plus qz plus r, where p, q, and r are constants. And what he shows is that you can solve this 4th degree equation or a similar 3rd degree equation by intersecting circles with a fixed parabola. If I remember, I don't want to go through this. He has one parabola by a complicated construction involving these numbers. He constructs a second circle. He continues, and he has to do different things according as to the signs of P, Q, and R. He continues, and I think he ends up from that diagram. He goes over to this. He constructs a second circle, and then if there are 4 roots of the 4th degree equation, those 4 roots are these 4 lanes. 2 would be negative and 2 would be positive. So that's the kind of thing that Descartes does in the section on geometry. And I've seen it suggested that he was the first to do that kind of thing, and it's not unamusing. He does it, he uses, for equations of 5th and 6th degree, it's probably the wrong way to take. He does it. Equation of 5th and 6th degree using moving parabolas, but that's probably unwise. So what's our conclusion? So after this digression on Descartes, is that if a geometric construction, I'll read it here, that's easier than looking at it. You can read it yourself, but it requires in its analytic form nothing but addition, subtraction, multiplication, division, and the extraction of square root, then it can be achieved with ruler and compass, and conversely. Now, the results that you end up with could be very complicated. In other words, you could start up, everything is done in terms of the coordinates of some collection of points that you're given at the very beginning. For example, you could be given 2 points, A and B, AB and CD, and then what we know then, on the basis of what we've done, is that solely with the ruler and compass, we could form this number, if we cared to. I mean, we'd like to do something a little bit more systematic than forming random numbers, but that's what we can do. And the numbers that we get, for example, we obtain for the regular heptadecagon will be at least as complicated, but more systematic, because they'll have this geometric background, namely there'll be this pretty object, the regular 17-sided pentagon, in the background. All right, so that's analytic geometry done with. And then next, the prerequisite is complex numbers. So let's spend a little time on complex numbers and then go on. So, by the way, how many, just out of curiosity, I know that, is there anybody who hasn't seen complex numbers in the room? Okay. I know at least one person who hasn't, to the best of my knowledge, hasn't seen them, but I won't reveal who that person is. All right. So, if everyone has seen them, then we can go over this page fairly fast. Namely, you all know that when you set about solving a quadratic equation, this is the general formula. And it sometimes happens that b squared minus 4ac is negative. That means it sometimes happens that you're taking the square root of a negative number. And since all the numbers that you meet with before you meet complex numbers, or fractions, for example, but not only fractions, have the property that the square is positive, you're going to have trouble in taking the square root of a negative number unless you introduce arbitrarily and conventionally that square root. So we're forced to introduce the square root of negative numbers, at least formally, if we want to be able to solve all equations. That means, in particular, we have to introduce the square root of minus 1. Now, what this relation says, that square root of any of minus c is equal to the square root of minus 1 times the square root of c, so it's equal to the square root of minus 1 times the square root of c. taken the step of introducing the square root of minus 1, and we allow ourselves to multiply by other numbers, then we're necessarily going to get the square root of any negative number. Now that's a very useful fact already. So what we need, however, in order to solve any equation, we have to be prepared, something like this, to take a real number, that would be the first part, another real number times the square root of minus 1 for the second part. Sometimes this wouldn't be, if this were positive, that wouldn't be necessary, but in the case that b squared minus 4ac is negative, that's necessary. So in order to solve this simple quadratic equation, we have to introduce numbers of this type, and those are complex numbers. So it is a remarkable fact. I actually had this discussion with a young physicist over the summer. The reason for the discussion are not so important than trying to make the distinction between an invention, a discovery, and a theory. And it seemed to me that complex numbers were, in some sense, a trick, an invention. And he objected, as a physicist, to this. But it seems to me that even as a mathematician, it's rather, if one thinks only of mathematics, it's rather surprising that by introducing just these numbers for the sake of solving quadratic equations, one can then solve any equation. That's, even as a mathematician, I could think about that for a while. We all know it, and we know it's not so easy to prove, but think of it as natural. It's actually even a little surprising. All right, so since you all know about complex numbers, there's no one is willing to admit it. You have to know about complex numbers. We can be fast here. So we have to be able to multiply them, and we have to be able to add them, subtract them, and divide them. So for us, they're just symbols. This is an arbitrary, what a mathematician would call a real number. You can think of a real number any way you like. It's a decimal number with a ordinary decimal expansion. We have to add them, so we add the real parts, and we add the imaginary parts, and then we put them together to get the real part and the imaginary part. Multiplying, what we have to do is we just multiply out, right? We multiply a times c, a times di, bi times c, and bi times di. Then we have to remember that I squared is minus 1, so bdi squared is minus bd. We put those together. That's the real part. We have ad plus bc all times I. That's the imaginary part. So that's how we multiply them. That's how we add them. Subtraction is just the same, except we have a minus here and a minus here and a minus here. Division is more difficult, of course. Now, I don't know. Let me just say what you do. So if you want to divide a by c, that means you have to solve a equals ce. So that's a, that's c. So a is that, that's c, that's e. We want to solve this equation. We multiply both sides by c minus di. That's a trick, because c minus di times c plus di, we use this rule. We'll get in here something that's 0 because of this sign we've been clever enough to put in. We get c squared plus d squared. So c minus di, so we multiply c minus di here, just get c squared plus d squared times e plus fi. C minus di on the other side gives us whatever it gives us, a plus di times c minus di. But now we can easily divide by this. We just multiply this out, or we just take c squared plus d squared, ordinary number, and divide it into c, and divide it into d. Just do it that way. So e plus fi, the number we're looking for, we have to write as a plus bi times this funny looking thing. And this funny looking thing has the property that if you multiply it by c plus di, you get 1. In other words, over c plus di is that thing on the right. Everyone said he knew about this, so I'm going fast. And everyone then probably also knows about complex numbers and Cartesian geometry. So complex number is just a plus bi, and we can think of it as being the point with coordinates a and b. So here's the point 0 plus 0i, it's the origin of coordinates. 1 plus 0 times I would be there, it's the point with coordinates 1 and 0. The point with coordinates 0 and 1. 0 plus 1 times I. The point with coordinates 1, 1. 1 plus 1 times I. All right. So, I don't know. I'm afraid that, I'm a little afraid that not that even those, and I know that a lot of people certainly don't want to read too much about complex numbers, but there may be others, unfortunately didn't speak up, but they should have, who don't know about them, and that may have been too fast. But let's just think about it now. Think about them at a little slower pace now, and we'll come back to them next time. And we don't have too much time left today, and that means anyone who regrets saying he knew about complex numbers can let me know in intervening time, and I'll review briefly next time, because it is important for our purposes. It is critical that we have some idea of what they are. So unit circle means a circle of radius 1. And when we set about constructing our regular figures, we're always going to inscribe them in that circle. So we're always going to be looking for points. Our regular pentagon, our regular 17-sided figure will have vertices that are on that circle. So their vertices can be thought of as particular complex numbers, namely complex numbers, on that circle. Now, what are these complex numbers like? Well, remember, if this is an angle theta, that's on the unit circle. This height is sine theta, and this length here is cosine theta. So that means the point has coordinates cosine theta plus I sine theta. And what happens now when we just think of this as a complex number and multiply some other complex number by x plus y, by it? Now, this is the other complex number. First coordinate x, second coordinate y. This is the real part, if you like, this is the imaginary part. Multiply it out. We get cosine theta times x, that's that. Sine theta times y times I squared, which is minus 1. So minus sine theta y. Then we get I sine theta x, so sine theta x, and cosine theta y with an I, so plus I times cosine theta y. So we get a point whose complex number, whose first coordinate is this, and the second coordinate is that. In other words, according to a formula that I stressed beforehand, this number is just this original point rotated through the angle theta. So all we've done here, it's an important fact, is multiplying by this complex number, whose distance from the origin is 1, we've just succeeded in rotating the point xy through the angle theta. So if this was a point xy, multiplication would send it over here. So, and in particular, if we take another number of the same type with some other angle phi, and we multiply these things together, we get cosine theta, x is now cosine phi, minus sine theta sine phi. Now, when I discuss rotation, I didn't bring the transparency today, but when I discuss rotation, I reminded you of the formula for the cosine for the sum of two angles. Cosine of the sum of theta and phi, so cosine theta times cosine phi minus the sine theta sine phi. So in other words, this just using that, so if I multiply out the real part is this times this, minus sine theta times sine phi is that. The imaginary part, so we get I sine theta cosine phi. We also get I sine theta cosine phi. So we get I cosine theta sine phi plus sine theta cosine phi. And I stressed before in the course of the discussion that that was the sine of the sum of those two angles. So we have this formula, which allows us to do the following. Particularly allows us to take, in this formula we can take phi equal to theta, then this side is just this number squared, and we get cosine 2 theta plus I sine 2 theta. In other words, this complex number squared is this complex number. So we know how to take the square root of certain kinds of complex numbers, so that we're doing just fine. We know how to take the square. We know how to take the square root of this number. The square root of this number is just what we have here under the square. If I just think of theta, that's an arbitrary. Theta is arbitrary. It's an arbitrary angle. And that means 2 theta is again just an arbitrary angle. So call that arbitrary angle 2 theta theta. I hope you don't mind that. And then one way to rewrite this equation is this. Just thinking of 2 theta as being any old angle. Particular 2 theta could be, if I written phi here, it would have been better. Phi equals 2 theta, this would be cosine phi over 2 plus sine phi over 2, I sine phi over 2, all squared. Cosine phi plus I sine phi. So we can take, in our terms, you see, what we see is something that we see that taking the square root, at least, of this particular kind of complex number is a geometric operation. It's that of bisecting an angle. So we did discuss particular bisecting an angle. It can be done with a ruler and compass, and I would say that more of you have bisected an angle using a ruler and compass than have discussed complex numbers. Right? So from that I infer that you have all bisected an angle using ruler and compass. So up until now, you see, we could only take square roots of positive numbers, really, with ruler and compass. But now we know that we can take the square root of even some complex numbers with ruler and compass. We certainly can add and subtract and multiply and divide them, because that's just a matter of adding, subtracting, multiplying, and dividing their coordinates, as we've seen. But we can actually take the square root. Now, you could guess from this that we could take the square root of just any complex number. And here's my any complex number sitting out here. There's coordinates x and y. And then this b, it lies on the unit circle, so it has coordinates cosine theta and sine theta. And that means, I should have drawn that in. There's similar triangles, but we've done this before. X is to sine theta. X, this distance, is to cosine theta, as y is to sine theta, and that means x and y, these two, x is equal to some number r cosine theta, and y equals some number r sine theta, and this r is just this distance over the unit distance. In other words, r is just that distance. So, can we take the square root of x plus iy? X plus iy is r times this number. We can take the square root of r, that's the square root of r. We can take the square root of this, so we can take the square root of the product. All right? So, now what this means is that we don't have to worry when we perform our algebraic constructions in the future whether we're performing them on real numbers or complex numbers. We're just going to be taking square roots, and this square roots of a complex number is also something that we can do with ruler and compass, because all it involves is to take the square root of this positive number r and to bisect the angle theta. And these are something that we can do geometrically. So that means that what I said earlier is now true for complex numbers as well. And all right, I think with that said, what we can do, I'm moving along just a little bit faster than I hoped. That means I might even get through Gauss in 3 more times. What we can do next time now is begin to discuss algebraically the regular pentagon. And once you've discussed algebraically the regular pentagon, you will be in a position, I think, to do the regular heptadecagon as an exercise, but nonetheless, we should have 2 weeks left, and in those 2 weeks I'll do it too, following Gauss. But my hour is up for today. And as I said, if anyone wants the copies of, here are copies of the transparencies in my comments, he should give me his name and or address.